All right, 12 o'clock. Let's get started. And welcome to lecture 24, November 23rd. So just last day before the Thanksgiving break. So we are almost there. I'm hoping you are looking forward. And we have 52 people on the call, which is pretty amazing given that it's 53, 54, given that it's the last day of classes in the week. So how you folks are doing? Good. Okay. Good. Heading home tonight. So excited. I can definitely relate to that. Doing great. Good. Hopefully, you all enjoy your Thanksgiving break and do something fun and visit your families. All right. So, and I see a discussion going on in chat about the homework. So let me start with this then. So yes, as I was suspecting, I was able to verify my suspicion, and the problem 4.5 was in fact just copy pasted from the wrong version of their textbook. So it was from a RISC V version, so from a totally different architecture. So instead of replacing this problem with a correct problem just from the previous edition of the MIPS version of the book, so I decided just to scrap it, and so let's make it a little easier on you. So I think it's perfectly fine. Right. So no problem 4.5. You are welcome to submit it if you want, but it's not going to be graded. So it's just going to be 3 problems. All right, so that was the first piece of news, and then let me start sharing something. All right, and we have a test question in the Q&A. So all panelists, please identify yourself, answer something so that we know you are here at the beginning of the lecture at least, and hopefully you stay through the entire lecture. All right, so that's it. And for homework 6, their deadline has been extended, but we already talked about it, so it's due on the 29th. Submission page is open, and I actually noticed someone already submitted and got almost full credit. Just missing, I think, like 2 points on one of the hidden test cases, and it's not because that hidden test case is something obscure. It was just because it looks like there are some memory issue, and towards the end of the output, the program just is just starting to to print garbage. So that's probably something related to going beyond their string, the string limits when printing a string, or something like that. All right, and yeah, textbook problem 4.5 removed. And so that's all about homework 6. And then project, all groups are formed, so no more groups can be made. If anyone didn't join the group, they're going to be working alone. And unfortunately, I think unfortunately, there was a number of students who didn't join any groups. So, but it's that's it. All right, so the deadline has passed. And then we had some very creative group names. So I made a poll. Did Prof find any group? Well, one group invited me to their group. So and they sent me an invite. So that was very nice of them. But I had to politely decline. All right. So this poll number 1 is just vote for the group name that you liked most, and some of them were pretty funny. I think some of them were referring obviously to our current Rensselaer president. So I don't know if you've heard the latest news. Their next president, the name of the next president of Rensselaer of RPI, the 19th president, has just been announced, and it's going to be Professor Martin A. Schmidt, current provost of MIT. Okay, so yeah, that's a bit of our news. And so that's pretty much it. So now let's get to one other thing about the project. So here's a little piece that I had in my notes like 3 lectures ago, and I think that just illustrates what we are trying to achieve with the project, and why we have those. And it was the same for the labs. Why we are trying to why we are limiting you in their C features that you're allowed to use, because the overall goal is to actually write a model, write a simulation that would be as close to the hardware as possible. There is no direct analogy for an if statement or a loop in hardware. Okay, so there are less direct analogies, and those are given here, right? So for example, if you have an if, we already learned, well, it's just a multiplexer, right? There are 2 alternatives, and then there is the selector signal that selects one of the 2. And similarly, for if statement with no else, it can be done like that. So just try to think in terms of hardware as you are designing your project, and that should help you get tuned with the overall idea of the project, and why what we are trying to enforce with this project, what we are trying you to learn. Okay, so that's that. All right, yeah, we're gonna restart with basically the pop quiz from last time. So this slide. So I think it's time to. Oh, one other thing that I wanted to mention. So I just wanted to, to pay my deepest respect to the people. I think that there are two folks who did something in Minecraft. So basically an adder with an ALU with A invert, B invert, all that, whole 9 yards. So I just looked at the screenshots, and it is looking pretty amazing. So please give it up. I made you an offer if I know if these people are here in this lecture today, but if you are, or if any of two of you is, then I made you an offer, make a presentation, in the last lecture about what you've done, and get the respect from everyone in the class, and earn a little bit of extra participation credit. So I think it would be justified. It would be worth it because I think it was a pretty cool initiative. Of course, it wasn't required and wasn't even expected, but I really respect you folks for still doing this without being promised any perks. So I think that is worth at least a thank you. All right, so we stopped, I believe, here, this pop quiz. So let me get my windows organized again. All right, if we look at the actual answers, I actually don't think they're the majority. The last time I looked, at least, I don't think the majority of students voted for the correct answer. So, and let me look at the old polls, and it was 2301. So this one, and the majority of people voted for number 7. Okay, for 7. So for 7 cycles, that it would take this sequence of instructions to complete. And I think that's not the answer I had. So let's go back to our pop quiz. Okay, so we first, so of course everything hinges on the idea that there will be data hazards, right? So there are some data dependencies that would prevent these 3 instructions from proceeding without any bubbles, without stalling the pipeline. So if we didn't have any stalls, how long would it take to execute these instructions? These 3 instructions, from the time we start IF for the first instruction until we are done with WB for the second instruction. It's 7, exactly, right? Because first instruction will be done in 5 cycles, right? We know it's 5 stages. And then, next cycle number 6, LW will be done, and then next cycle, so cycle number 7, add will, the second add will be done. So in their absence of data hazards, it would take 7 clock cycles. And if we have some hazards, then that would require that we stall the pipeline. It would be more. Okay, so yeah, exactly. There is a hazard here. Well, I don't know. 7 is just their majority vote. So it's a pop quiz from last time, and the majority of people voted, I believe, for 7. So, and I'm wondering too where 7 is coming from, right? Why most people thought this one, right? Am I looking at? Yeah, 24 people voted for 7, more than for 8. Okay, and yeah, so 5 and 6, obviously, hopefully, you see by now that these 2 options could have been eliminated, because in the best possible scenario, it couldn't, 3 instructions cannot be done in 5 or 6 clock cycles. Okay, and so then if we have a data hazard, and we do on T2, as someone already indicated, right? So add will write to T2, and then LW is going to read T2 because it will be the base address for their memory access, for the data memory access. So obviously there's a hazard right there, and so it's going to be at least 8 and maybe more, but we shall see once we plot our multi-cycle diagram. So exactly the way to solve it was to build a diagram which is very similar to what you need to produce in your homework. And here we just use a slightly different abbreviations for the phases. And I actually have it right here. Okay, and so fetch, decode, execute memory, and write back. And we see that in this case, yeah, it's sufficient to have just one stall, and we are not putting F and D here, but it doesn't really matter. So we put all 5 stars here, which is again the format is very very slightly different from your homework, but the end result would be the same, right? So it takes all in all 8 clock cycles to execute these instructions. Okay, so yeah, please make sure you see those dependencies, right? T2 here, and so T2 here, and here is the dependency with T2 here, and all right, so. Yeah, and there is also forwarding here. That's why we we only have to do one bubble. All right. So next thing then let's look at their diagram, and we already talked about this single cycle pipeline diagram, right? It's a snapshot of their processor, and we only are looking at really their one cycle, but then different instructions would be at different stages of their execution during that cycle. Okay, and this is exactly what we show. And here, between those ticks, we show, roughly their extent of their hardware that is used by each of their stages, each of the phases. And so we see that, yes, currently in this pipeline in our data path, we have 5 instructions at different stages of execution. This instruction add is just entering the pipeline. It is being fetched, whereas this instruction right here is about to leave the pipeline, right? So it is really like a pipeline, right? So if you want this analogy, right? So here is here is instructions flowing in, and in this pipeline we can think of like the pipeline having 5 sections, right? So the flow going in goes through all 5 stages sequentially, and then it leaves leaves our pipeline, and when it is done. All right, so now of course we have to complicate things again. We have to add control signals, right? So the previous diagram makes sense. There's nothing wrong with it except that it kind of avoids mentioning the control signals, and we know we're gonna need them, right? So for the majority of hardware components that we are talking about, we do need all those control signals. And so let me actually move my windows again so that I can see what people are saying. And yes, so someone says the control signals can go along with the instruction data. Exactly. So we need to keep the control signals saved in our buffers, in those registers that are in between the stages. Exactly. And we will see this shortly. Okay, so this is a simplified pipeline control. So it just shows their control signals that we need, right, without really explaining where they're coming from, just identifying the control signals. And here we have our famous blue oval that produces all those signals. And once produced, they have to travel with their instruction. Okay, so we know that initially here we have the instruction word, and then we might be adding additional stuff to their to our buffer. So, for example, once we read their registers, so read register 1, register 2. Remember, we were storing them in this register, in this buffer as well, so that it could be used later. So it travels with instruction, and the same goes for all the control signals. Okay, so we first, when we produce the all the control signals, it happens at the ID stage. Okay, and that's why they enter this buffer, this register that we call IDEX, that separates the ID and EX stage. And here we classify all control signals into those that are needed for the write back stage, the memory stage, and the EX stage. Those are the three stages that are remaining after ID stage. Okay, because control signals themselves are produced during the ID stage. All right, so for the EX stage, we need all three groups of control signals. Well, for the EX itself, we only need this, right? But we have to store the M signals, so signals for control signals for the M memory stage and for the write back stage as well, just because they're going to be needed later on for stages that come after execution. Okay, so once, and of course here we have, this is the execution stage, right? This was the ID stage, and this is the IF stage, and this is the MEM stage, and this is the write back stage. So once we are done with their EX stage, we no longer need to store, to keep their control signals that are needed for EX stage. We are done with it. And that's why we only pass along to the next register, EX MEM. We only pass the instructions that are needed for the following stages. So for M, memory, which is the immediately next stage, and write back, which is not going to be used immediately, but will be used later in the last stage, write back. Right, and then similar, of course, after MEM stage, we no longer need to keep it, so we just do not carry those memory control signals forward. We just keep write back because they are needed for the last stage. All right, and so this is the whole thing. So this is the pipelined data path diagram with control. So here's just everything brought together. So there are really nothing new except for control signals now need to be part of those registers that separate the stages. All right, so you think that's it? You think we are done here? Well, how many of you think we are done? And that's the end of it, and it's not going to get any more complicated. Yeah, it's never done. You got that right. So what we do not have implemented here yet. Yeah, I think it would be naive to expect this. Yeah, unfortunately. So we do not have anything related to forwarding here yet. Okay, so we still have to implement forwarding, and that's the next level of complications that we are going to have here. All right, so let's actually talk about kind of come back and reiterate over data hazards and talk about forwarding and stalling. So those are two pretty much opposite things, right? So if we want to avoid stalling, we implement forwarding, and as we discussed before, in at least there are some cases where by using forwarding, we were avoiding stalling altogether. However, we also saw an example when forwarding was not enough. So we had a load use hazard where by using forwarding, we were able to eliminate one of two bubbles, but not two. So not both. So stalling was still necessary. All right, so let's look at this example. It's a data hazard as follows from the name. And so obviously we have the following dependencies. So sub writes to S2, well, register 2, and not S2, $2, second register. And then and reads from this register, and then or reads from this register, and then add reads from this register. So they're all dependencies right here. Okay, and then SW reads from this register, right? So we all have all those dependencies. Some of them are very innocent. Obviously, there's nothing wrong with SW reading this register 2 written by sub, because they are separated by 3 other instructions. So clearly, register 2 would be already written by sub by the time store word reads it. So that's obviously not a problem, but this is to demonstrate that we might have multiple dependencies, and we need to have some rule, some formula that would allow us to detect the need to forward. Okay, so before we discuss how forwarding is done, we need, of course, to decide when forwarding is necessary. So far, we discussed, when forwarding is necessary based on drawing the arrows like that. But obviously, if you want to really implement it in hardware, you need something more formal, right? So you need to go from reasoning to a specific formula or specific implementation. That's exactly what we are going to do. All right, so and to derive the formula for forwarding, we need to kind of again go back a little bit, and this is the same example that we had here. And look at all the dependencies which I drew on the previous slide. Here they are shown with those blue lines here. Those are all the dependencies, and we see that some of them. So if we look at, right, so there are 5 instructions, and first instruction writes to S2, and the remaining 4 instructions, they all read from S2. So there's got to be 5 links or 5 lines that indicate dependency, right, from the first instruction to each of their other 4 instructions. And some of those lines go vertically or kind of go from left to right. In particular, and let me choose a different color. In particular, this line goes vertically, and this one goes kind of left to right. Of course, it's still vertical, right? Because the instruction, the following instruction is lower, but it's kind of going left to right if you look at just the axis dimension. And we know when it's left to right, it's forward in time, so there is no issue ever. Okay, and that's why we are good, right? There's nothing we need to do about it. If our dependencies appear to kind of go backwards in time, then it's a problem, right? So this one goes from right to left. This one goes from right to left in time. Remember, our time is here. So clock cycle 1, clock cycle 2. This is essentially our time, just in clock cycle instead of picoseconds. And obviously, this is a problem which we can verify that it is by just trying any specific value that is in register 2. So let's say it's 10. It's 10 here until it is written back in clock cycle 5. So in clock cycle 5, in the beginning of clock cycle 5, the value in register 2 is still 10, and it is written. So we know that right uses their left, uses their first half of the cycle. So around around half through this cycle, right, we know that the value in register 2 will change from 10 to -20, due to the effect of writing back, right? Sub will be writing back register 2. And then from this point on, of course, it's going to be -20 because no other instruction in our sample changes to 2. changes register 2. And so obviously the problem is with these two instructions that have the dependency that kind of calls for going back in time, accessing their value before it was actually written to the register. And we know that we can solve this with forwarding, right? So the value that will be eventually written to register 2, it is computed at this stage here, right? So this is when the value, right, is computed by our ALU. So at this point, we know what that value is. It hasn't been written to register 2 yet, but we know at least what that value is. If we didn't know what the value is, there's nothing we would be able to do. But once we know what the value is, we can forward it to their ALU for the next instruction, so that at least the next instruction can proceed with adding their contents of 2 and 5, and that would solve it, right? So really, this AND doesn't insist that its value to be read from register 2. It just needs to know what that value is, even if it technically does not read it from register 2. And that's the whole idea behind forwarding. And so for the second dependency, we have, we see that it's kind of the same thing. The value needed for the ALU of OR instruction here no later than this moment of time. And at this moment, the value has been computed by the first instruction, but hasn't been written to the register. So again, by using forwarding, following this connection, so it has to be an additional hardware connection, we can, fast forward this value to the ALU. So let me see, what is DM doing for sub? DM is not doing anything. Note how, and let me try some other color. See, if you look at DM, make sure you understand all the conventions used by this diagram and by the figures in the textbook. DM is, has this white transparent background. It's not shaded, which means it's not used by this instruction. And contrast it with SW, which you can see that yes, it writes DM, right? Because the left part of the component is shaded, which means writing happens. Okay, so yes, DM is not used. Data memory is not used in execution of the sub instruction, but we still have to go through this stage. Remember, we cannot skip stages. Only LW and SW go through DM. Correct. One writes, another reads. Yep. Yeah, and that's exactly the problem. Like if sub could somehow skip this memory stage, and during clock cycle 4 it would write back the result into register 2, then our second hazard would simply not exist, right? Because by this moment of time the value would already be in register 2, and then that's it. Our OR instruction would just read it normally. Okay, but because sub or any other instruction is not able to skip any stages, it has to go through this stage in which technical instruction is really not changing anything in the state of the processor or memory, right? But it has to go through this stage, memory. And that means that when we arrive at the end of clock cycle 4, the value, this difference between registers 1 and 3, it has been computed, but it hasn't been written into the register, and that creates a hazard with the OR instruction. All right, so and based on this, here are the formulas. So the formulas that that allow us to actually implement their flag that would tell us that the forwarding is needed. Okay, so we pass register numbers along the pipeline as we have seen in those registers that are between the stages. So for example, if we have, let me switch to my red, right? So if we have IDEX, it will have one of the parts of the IDEX register would be register RS. So that would be register number for RS for the instruction that currently sits in the IDEX register. So here's a quick question. How many bits is register RS? How many bits would it? Yeah, it's 5 bits exactly. Thank you. Right, because we need 5 bits to encode each of the general purpose registers are that we in their general instruction format we denote as RS, RT, and RD. Each is 5 bits because we have 32 general purpose registers. So ALU operand register numbers in EX stage would be similarly given by register RS, register RT, right? But please pay attention to which register this field, register RS, register RT, is part of. Okay, so now we can sort of classify all our cases which lead to data hazards into these first 2 categories, and then there will be 2 subcategories inside each of their category. So if we have in the EX mem register D, right? D is destination, which is the same as either RS or RT of the instruction in the IDEX sitting in the IDEX register. That's a hazard, right? So that's something that would require forwarding. And again, we can always go up here. So which register is this? All right. So let's mark them. So what is the name of this register? This gray stick here that I'm going over. Exactly. This is IF ID. And of course it's for the first instruction, right? So this is ID EX. This is EX mem, and so forth. Of course, for the second instruction, right? This is IF ID. This is ID EX, and so forth. So we see that yes, the reason why we were able to detect the hazard is that EX mem of this, okay, has the same destination register as one of the source registers for IDEX here, right? So EX mem, and we can verify EX mem RD, right? So this is destination, like our register 2 is the destination, right? So it will be stored here, right? RD, and IDEX either RS or a T here. Okay. Wait, I'm right. That never happens. Oh, okay. Yeah, you are right. Of course. All right. So these are first 2 cases, right? That only differ in which of the source registers we consider, right? Because there might be one of 2, RS or a T. And then the other case is also illustrated in our diagram here. So this register here is mem right back. Okay. And so it goes, so this thing here is IDEX. Okay. So, and it kind of makes sense because we see that this hazard is not between the instructions that are next to each other, but it's the hazard between the instructions that are separated by one other instruction. So there would be, the registers that we have to consider would not be the registers kind of next to each other, but it would be registers from the stages which are one stage apart. So it would be IDEX and MEMWB. So MEMWB, again, for RD, and then IDEX for either RS or RT. This is our second case, right? So when we forward from the MEMWB pipeline register to their ALU of their, well, we only have this one ALU which is engaged in EX stage, right? Okay, so that's hopefully explains where those formulas are coming from. So if you don't really have to memorize it. Of course, on the exam you're welcome to print anything you want, but if you didn't and you couldn't memorize it, just come up with an example that shows this, and then you should be able to reconstruct this multi-cycle clock diagram, and from these two cases of forwarding, you should be able to reconstruct the formulas. All right, so that's almost it, but there is a catch. So we only need to forward an instruction when there is an actual write into the register. Okay, because if we're not writing into the register, then of course it's it's not a hazard, right? The hazard only happens when we are writing into the register that will be then read by one of the following instructions. So how do we know whether we are writing or not? Well, that's why we spend so much time on control signals, right? So we have reg write, which we carry along with all other control signals. So first into EXMEM pipeline register, and then into MEMWB pipeline register. So we only need to forward if reg write is 1, and only if RD, the destination register for that instruction, is not 0. Right. So remember that somewhat special register. It's still a general purpose register, but it is accessible to us programmatically. So remember, register with number 0, which we typically use the mnemonic $0. It is a register that is guaranteed to contain 0. So just a 32-bit word, which is 0, like 0, 0, 0, 0, 0, 0, 0, 0, right? So that's the contents of this register. If we attempt to write into that register, we are not going to get any kind of error or exception or anything like that, right? So any instruction that is capable of writing to register, like all your R-type instructions, for example, they can have 0 register as the destination register, right? So it is allowed. It is you're not going to get, like I said, any error or anything. It's just not going to work. Okay, yeah. So Shane mentioned that that's not going to work, but silently, right? Basically, if you have something like add 0 T1 T2, this instruction will execute successfully, but it will have no effect because whatever the sum of T1 and T2 is, it's going to be lost, right? The contents of this register is not going to change. It is going to be 0 as it was before. So effectively, this instruction is equivalent to a NOP. It is guaranteed to not have any side effect, any effects at all on the processor. Data memory doesn't change as the result of this instruction. Registers do not change as the result of this instruction. So it is essentially a NOP, right? Semantically, it's a NOP. It's of course not going to be the same instruction code. So for NOP, the instruction code is actually all zeros, right? For add, their instruction word is not going to be all zeros, right? Because at least we have those registers encoded and they are not zeros, right? So their numbers, their codes are not zeros. So this word is not going to be all zeros. Okay, but essentially this instruction it would have the same effect as NOP. So long story short, we need to make sure that the destination register is not 0, because if it is, we are attempting to change the 0 register, and there's no need to forward because we know this instruction would have no effect, right? So if our instruction above this example, had add, which wrote into T1, and whatever the arguments were, doesn't really matter. T1, right? So like normally we would be willing to forward this T1 so that it is available here. But if the destination register is 0, we don't care, because this sum of T1 and T2, we don't even have to compute it, or we can compute it incorrectly. It doesn't matter. It's not going to affect anything. In situations other than these, when forwarding can work, do we need to resort to stalling to account for hazards, or are there other methods? So if we cannot prevent stalls, then with forwarding we have to stall. Okay, so we already saw an example when forwarding is not enough. Okay, so recall this load use example. Okay, so with forwarding, if we can make it work so that it eliminates all hazards and we don't have to stall the pipeline, perfect. But it's not guaranteed to be so. There are instructions for which it would not be possible. Did I answer your question? And no, there are no other methods to prevent stalls other than forwarding in hardware. I mean, in software, if your compiler can rearrange the instructions so that the instructions are now separated by some other instructions and the hazard simply doesn't exist, of course that's perfect, right? So if you could spread apart your load and use instructions so that there are two instructions between them, of course you're not going to have any stalls, right? But that's not something that can be done by hardware, because hardware cannot just arbitrarily rearrange instructions. It's it's too low level. It has no knowledge of what is going on. It has no way of guaranteeing that rearranging instructions would not alter the semantics of the problem. Whereas the compiler is much higher level, is in that sense much more intelligent. It can actually rearrange instructions because it can guaranteed can compute that doing so would not alter the semantics of the program. All right, so here we are, right? So, and we have, of course, because we had two subcases of stalling, right? So with EXMEM or MEMWB, of course, we have to have them here as two entries checking that register ID is not 0. All right, and forwarding paths, here we are. It just shows the outline of this forwarding unit, which is going to be, quite predictably, hopefully you expected it. It's just going to be a bunch of gates that implement the formula that we had above. Okay, so, it's going to be a little bit more complicated, right? It's not even a formula. The real formula would be similar to an if-else kind of statement, right? But we are getting there. So, and we just talked with you about like what do you do if you need to do if-else in hardware, right? Usually you just use a multiplexer for this purpose, or something else just that you can do with even elementary gates, right? And that includes multiplexer, right? Multiplexer you can implement with elementary gates. So here are the inputs, right? So those are register RD from both pipeline registers, and it's pointing here, right? So those are inputs, and RS and RT from IDEX, right? That's all the things that are mentioned. And now we have two flags, two control signals, two outputs that we call forward A, forward B, because they correspond to our two cases here, case number 1 A and B, and case number 2 A and B, right? That's why we need two control signals, forward A, forward B. Is this related to why I said being advised to not use mult div too soon after the last time the instruction was used? I'm not sure. If you give me a little bit more context, like who you were advised by, and maybe like a specific example, that would probably make it easier. Without an example, I'm not really seeing how it would be different from the examples that we are reviewing. So, but please feel free to follow up on this on the Submitty forum. Okay, let's just take it offline so that we're not wasting too much time on this. All right. So the forwarding unit checks whether any of the cases trigger, and if the cases trigger, it cannot forward or it can. It can forward. So forward B is 1 when we forward. Forward A is 1 when we forward. And you will see shortly that these cases are actually mutually exclusive, right? They cannot happen at the same time. So we either forward here, all right, between any two given instructions, or we forward here, right? We cannot forward both for the same pair of instructions. So when the case is triggered, you forward. Yes, you're correct. So this forward A or forward B would be 1. Okay, and that means that we forward because that would mean that we we switch this multiplexer, and just a quick sanity check. Forward A and forward B, is it a single wire or is it more than one wire? Each of forward A, forward B, just one single wire, one wire, more than one. All right. Wait, it's 2 exactly. Look, we have 3 inputs into the multiplexer. So the selector, it's got to be 2 wires, right? At least. Well, we don't need more than 2, right? But it's got to be 2 wires. It's a 4 multiplexer with a 4th input that is not used, so we can, think of it, being constant 0 or whatever, but it's a 4 multiplexer, exactly. All right. So, pay attention to these little things because they help you kind of do sanity check and, help you when you are doing your diagrams. And someone mentioned something about the future exam. You wanted this. Let me scroll up. This is going to be question 4 on the exam. Could be. I don't know. I haven't written it yet, but yeah, I'm thinking about exams constantly. All right, so forwarding conditions, here we are, right? We already kind of predicted that h of forward A, forward B is going to be 2 bits. So, and then we are just enumerating all the possibilities, and we have an explanation for them in this slide. So, right? So, when this forward A that we generate, this control signal that we generate is 0, 0, it means the first ALU operand comes from the register file. Okay, if so, there is no forwarding, right? If forward A is 1, 0, it means that the first ALU operand is forwarded from the prior ALU result, which means we are forwarding. And then, now our second case, right? So again, this, right? So this is, kind of my favorite, Roman numeral 1 and Roman numeral 2. Right? So two cases, 2 major cases, right? So we see this is number 1, this is number 2. Okay, so the first ALU operand is forwarded from data memory, or to or an early ALU result. All right, and so then forward B is pretty much the same, just for the second, right? So here's the difference: first, ALU operand, second, and second. All other things being equal. All right, 0, 0, 1, 0, 0, 1, but it's forward B instead of forward A, right? That's the difference. So forward A determines what gets to the first ALU operand, right? As we see, yeah, it's this first or top or upper ALU operand. This one is decided by forward A, and the second or bottom is decided by forward B. All right, and yeah, so forward A and forward B account for both multiplexers. Yeah, I'm glad it is making sense to you, right? So why don't we have forward A, which would be 1, 1, and 1? Well, this is exactly what we also predicted, right? For the same pair of instruction, you cannot have forwarding, both, right? So we cannot have both forward here and here, right? Because those are 2 mutually exclusive cases, right? Within, this Roman numeral 1, we cannot have both, right? Within the cases, not within each case, but across the cases, we cannot have 1 and 2 at the same time for the same pair of instructions. Okay, and that's why we cannot have 1 and 1, because that would mean like oh, it's 1 and 2, and that is not that is not possible. Okay, so 1 1 would not be a valid state for our forwarding control signals, right? So think about it as implementing forward A and forward B, right? You need to make sure that there is no way forward A and forward B can be 1 1. Is it currently possible? We shall see. All right, here's our next pop quiz, and the question is, can we always forward our way around instruction dependencies? And let me open that quiz. It is here now, and all right, 56 people voted for their favorite team name. That's impressive. I'm really intrigued which name would be the winner. What would be like the top 3 choices? All right, so next thing, turns out things can be even more complicated. And let me see. Like, you can't have 2 instructions going through EX at the same time. You do one after the other. Exactly. So you cannot have 2 instructions where you would need to forward from their EX stage and their MEM stage at the same time. How do you answer none of the above to a true/false question? It's just for fun. And certain things are not binary, right? We are used to thinking about many things as a binary, and sometimes we have just to rethink this as time goes by. Right? So for the longest time, gender was thought of being binary, male, female, and that's it, no other choices. But over time we learned that there are more. The spectrum is much wider. So maybe the same thing happens to true false. All right. So yeah, 50 Shades of Blue. I like it. I like the reference. All right. So here we have a data hazard. No doubts about that, right? So we have this instruction that is writing to register 1, which is being read by the second instruction. And then look, here is this writing to register 1 again. And now this poor third instruction, right? This one. Okay, it is all confused because there are 2 options, right? It can attempt to forward from here, or it can attempt to forward from here. Okay, so kind of both hazards occur, and this poor third instruction, it cannot decide which value would be the correct value to forward. Okay, so we obviously see from the semantics of the program that this one is wrong, right? This should not happen. So we should forward this result that the second instruction writes, not the result that the first instruction writes. And we want to use the most recent, just like our slide says, and that's why we need to revise our MEM hazard condition to say that we only forward if EX hazard condition isn't true. Okay, this is exactly this mutual exclusive thing for 2 cases, Roman numeral 1, Roman numeral 2, right? If we have a case which would trigger both of them to be true, we have to prevent it. Otherwise, we see this example, double data hazard. It's not going to work correctly if we try to do both. Right? We definitely cannot allow both. It has to be one or the other. And between these 2, we see that one is correct. Forwarding this value is correct. Forwarding this value would not be correct given the semantics of the program. All right. So here we are, a revised forwarding condition. Right. So this is what you probably want to put on your crib sheet. Right. So, but this is, if you don't, you should be able to reconstruct it from just the logic of everything that we discussed, right? So all the pieces brought together. If reg write is 1, so we are writing to the register, and this register is not register 0, and so this is the condition that we are adding to make sure that we are not trying to do Roman numeral 1 and Roman numeral 2 at the same time. And we have the fact that, yes, indeed, one of their source registers is the same as their destination register of that other instruction. Yes, we need to forward. All right, so forward A is 0, 1. And the other case, of course, is forward B. It's very similar, just instead of RS here, right, and RS here, we have RT here and RT here. All other things being the same. How would this work through gates? Well, this is exactly what you will be doing in there, kind of similar to what you are doing in the project, right? So an if can be implemented just as a multiplexer, right? So you have your condition, all right, this thing here as the selector signal, and then you are choosing between two choices, right? So, and we know that those choices are, well, 2 or more, right? So for port A, we know that the valid choices are 0, 1, 1, 0, and 0, 0. Okay, so 1, 1 is not a valid state. So you know that you need, you have basically 3 alternatives, okay? And you just need, you just need a multiplexer. What's the else cases for this? Well, it's if you're not, so this is forward A to be 0, 1. Okay, so the other cases would be forward A 1, 0 and 0, 0. Okay, is that making sense? So we discussed them here, right? So here are all the cases: 0, 0, no forwarding; 1, 0 from EX mem stage; 0, 1 from mem WB stage. So those are 3 alternatives. All right, and here is our data. How do you differentiate between 1, 0, and 0, 1 again? The difference is here. It's whether we have EX mem or mem WB. All right, and so here's our control with forwarding. Again, I don't think we've added much, but we to this diagram itself. But we discussed, we made it more precise what our forwarding unit is, what it does. Okay, and we now see that it will be getting, see this blue line here and this blue line here, right? This is the new stuff that we added based on our analysis. We want forward A to not be 1, 1, and 1, to guarantee that it's never 1, 1. Okay, and we need this additional signal. So this is this part. You see, this part of the formula is even in a slightly different color, right? So that explains why we need to grab those those connections from here and from here. All right, so what happens to load use data hazard? We talked about it before. We need to stall for 1 cycle, right? There's no way around it because we have this condition here, right? This relationship here, this relation here, and it goes backwards in time, right? It is like that. And the problem is there's no way we can forwarding can help us eliminate all their stalls. Why? Because it should make sense, right? So let's see. Load word reads value from memory given by this address computed as a base address plus the offset. So long story short, until the value that we need is extracted from data memory, which only happens here, we don't know what that value is. this value is not computed by the ALU as in our other example, right? If it were ALU, we could forward it. But if the value that we need, this instruction needs, right? This instruction reads second register, and the value is coming from data memory. So before this value is physically read from data memory, which happens in clock cycle 4, we just don't know what that value is. There's no way we can predict what is going to be read from the memory, and that's why we cannot really do anything about it. Yeah, you can only go forward in time. Exactly. You cannot go backwards unless you have a time machine. All right. So load use hazard detection. Why is it important? Because we know that's the case when, even with forwarding, we cannot avoid stalling their pipeline. So we check for those hazards, when the instruction is decoded, which happens at the ID stage, right? So the ALU operand register numbers in ID stage are given by those registers, right? So it's between IF and ID. So it's pipeline register IF ID, and we check RS and RT, and we know that it's going to be a load use hazard when this condition is true, right? So when we are reading from memory, right, mem read is true. This is a control signal, and when the RS register of the IFID stage is the same as RT register of the IDX stage, or that same RT of IDX is the same as RT of the IFID stage, right? So it looks, it looks like, a foreign language, but it should make sense. Again, if you go back to this diagram, right, and you just say, what is this register, right? This register is, so it happens after IF stage. So this ID stage, I'm sorry, so this is after ID, so this one is IDEX. What is this register? It happens after MEM, so this is MEM right back, right? So this one is EX MEM. This one is IF ID. So we know that, yes, it's IDEX register T, right? So here, and it's the same as IFID register SOT. So it's actually, we can even detect it much earlier, right? So here we don't have to let the problem, propagate until we're able to detect it. We can predict that there is a problem as soon as we decoded this instruction. So this is IDEX. And as soon as we have read this instruction, the second instruction, right? Remember, this register here, this is RT according to the format of LW. This is not RD. This is a destination register, but for load and store instructions, it is denoted as RT. Whereas this is RS and this is RT. All right. So these two registers. That's why we have, RT that are, from the same stage. So this corresponds. So right, this part corresponds to our LW instruction, and these are the choices for the registers on which we might have this load use data hazard in our AND instruction. Okay. So there are two cases, right? Because we can have this on this second register or on this register number 5, which is the second argument, right? If we had 5, here, right, it would be on RT and RT. All right. So if we detect a load use data hazard, what do? Nothing we can do. Absolutely nothing. We stall and insert a bubble. That's it. All right. So now the interesting question, probably one of the last interesting questions. How do we, what does it mean to stall physically in implementation hardware? How do we actually stall an instruction? How do we actually force an instruction to not have any side effects on the processor? And the answer is very easy. We just force all control values to 0. Okay, so EX, MEM, and WB will do a no operation. What about IF and ID? Right? Will they do no operation? No. So we start, all our instructions, they go through IFID, and we know that we can only detect that something is going on at the ID stage when we are like trying to read the register and it hasn't been written back by the previous instruction. So IF and ID will be not NOP, right? So we only need to 0 our control registers for these 3 remaining phases. Why does it work? Why is it not causing any problems that these two phases we executed as normally? Well, the thing is, if you think about their side effects or the overall effects of their instruction, any instruction, just reading the instruction from memory is not changing the registers, is not changing the memory. Decoding the instruction is not changing their data memory, is not changing their registers. So, we could do IF and ID as many times as we wanted. It's not going to break anything in the processor because it's not going to make any lasting effect. Whereas, and the same for EX, by the way, but MEM and write back, these are 2 stages, right? So these 2 stages are when we make some long-lasting effect on the state of the processor, because MEM can write to data memory, and that, of course, is is something that is not easily reversible, right? So this is an action that has a lasting effect, and write back changes the register file, and that, of course, is also an observable effect of an instruction. So these 2 effects are the only ones, right? So any instruction, the way we can tell whether an instruction executed or not is because it changed something either in the register file or in the data memory. Think about all instructions that all of them either change the register file or change the memory, or they change the control flow, like jumps and branches, right? They cause change in the PC, in the program counter. Okay, so that's why IF and ID stages are safe. And if our instructions started to execute IF and ID stages, and then at EX stage, for example, we decided to turn this instruction into a NOP and force all control signals to 0 starting from the EX stage, this instruction will not have any effect on the state of the processor. So it kind of never happened, right? So we can kind of stop this instruction from making any long-lasting changes to to their things that are observable to their register file and their data memory. And that's why we call it a NOP, a no operation, right? So their instruction word of their instruction is not going to change, but effectively we are turning this instruction into a NOP, into an instruction that is guaranteed to have no effect on the state of their system, memory, data memory, and register file. All right. So, this is just exactly what we discussed. This is a summary on the slide, right? So we prevent the update of the program counter, we prevent update of the IFID, and the instruction that we have in the pipeline register is decoded again. So IFID still has this instruction, right? We didn't flush IFID. The instruction is still there. We can decode it again. So we don't have to read it to fetch it again. And the following instruction is fetched again, IF. All right. And again, if you already started working on your homework, right? So you are recognizing things that kind of really refer to the diagram that you're supposed to produce in this homework. Okay. So one cycle stall allows MEM to read data for the load W. So again, this example is in in reference to our load use hazard detection, right? So, and of course, we subsequently can forward to the EX stage. So once we've read from memory, we got the value, and then we can forward it. We can forward it to their, to our ALU, so that we are avoiding the second stall. But one stall we cannot avoid. All right, and then how will the next instruction update? The next instruction will be fetched over and over again, as many times as we have stalls, right? So if the instruction that caused the bubble, it's going to be in ID stage repeatedly, right? And it works because this instruction is, the instruction word is in this pipeline register IFID. So the instruction has been fetched, so we can just keep decoding it until we can proceed. But the next instruction will be fetched and fetched and fetched over and over again from the same instruction memory, because every time we stall, we prevent update to the program counter. So next instruction will be fetching basically the same instruction that we fetched before, but we cannot proceed with that next instruction because we are stuck with this instruction that is at the ID stage. And until that instruction, can proceed, can get unstuck, can stop making bubbles, their following instruction would be stuck as well, right? It's the pipeline, it's the queue, right? The next instruction would not be able to proceed any further until their currently executing instruction at the ID stage frees up that ID stage and moves forward to their EX stage. All right, and so here's their your favorite multi-cycle clock diagram. All right, so this and that we read, note how it says, and this is very precise, and becomes a knob, right? We started it as an and, so we fetched the instruction here, we tried to decode, and then we realized, yeah, we cannot proceed because the value that we're going to need for the next stage, for the EX, is not even yet read from the data memory. So we turned this instruction into a knob, again without changing their. So this code here is still their code for their AND instruction, okay, and it's not changed to their to their code of the NOP, to the instruction word of their NOP instruction, but by zeroing all the control signals starting from here and here and here, we are preventing any damage, any changes to the state of their system that this instruction may produce. And that's why we call those bubbles, right? Because yes, the work is done, but this work is guaranteed to have no changes, to make no changes to data memory and no changes to the register file. And that's why we call it a stall, right? Because this instruction, yeah, it started executing normally, but then we had to kind of, dial it down and prevent it from making any lasting effect on the system, because we know the result would not be correct, because this AND does not know the values for one of the operands. And then when we try again on the next clock cycle, we have this instruction word already in our pipeline register. So actually here, this diagram is incorrect. Well, it's not entirely correct, I should say. Can someone point out what is missing, what is wrong? And I pretty much explained it. I stopped like really one sentence from the conclusion. So hopefully you should see what is missing, what is going on. It's about here and here. Anyone? Okay, so here we are, right? So this, well, more accurately, yeah, it's not this. Sorry, I confused you. I meant to underline, of course, this OR instruction, right? So this end instruction is stalled in the ID stage, right? So this this register is going to contain the instruction word of this end, right? And it's the same instruction word that is contained here, because really this knob is really this end. They are the same instruction, right? So the contents of the registers would be the same, but their following instruction is stalled in IF, and that's why we keep reading this IF, right? So IM is instruction memory, so effectively this is IF. So in clock cycle 3 we read this instruction, we fetched, or of course we didn't know that AND would get stalled, but then when AND got stalled, our instruction memory cannot just sit there and do nothing. So that's why we read it here, right? But initially we read this instruction here in clock cycle 3. Is something to do with the second bubble? No, there's only one bubble. Okay, because we use forwarding. Okay, without the use of forwarding, you would have 2 bubbles. And remember, in your homework, you have no forwarding. So that's it. All right. So, and the last thing that we added was this hazard detection unit, right? And you see that here is their input, all right? Input control signals, IDX, memread. We also have their data inputs. So this one is, if we track it, this is this, right? It's coming from this pipeline register. And then we have these 2 things. They are coming from this and this, right? So this is part of the instruction word, right? So they're coming from the instruction word. And this one is coming from the IFID. So this is exactly from the formula that we have written. And then we have to, we have to have this PC write control signal for the PC, so that when there is a hazard, we prevent PC from being updated. So when PC write is 0, it's not going to see its usual +4 increment, right? It's going to stay at the same value. And then we have IFID write control signals to prevent their next instruction from being written into IFID, right? Because if we are stalling, we want to keep IFID hold the instruction that is stuck, that is stalled at the ID stage. So the next instruction will be fetched from memory, but it will not write its instruction word into the IFID pipeline register. All right. Yeah, I haven't decided about the last homework. Yeah, I know I was planning on posting it tonight. Maybe I will be able to do that. I'll try to, but if not, definitely over the Thanksgiving break, I'll try to give you your homework, and I promise I will try to make it easy and short. Well, my easy and short. So please, don't hold your breath, but it's going to be, Kuzmin easy, Kuzmin short. So shorter, and easier than our typical homework. Okay, because I know it's the last one. All right. So summarizing, stalls are definitely not something good. Stalls reduce performance. But they are required so that our execution is correct. Okay, so first and foremost, we need to make sure that our program executes correctly, no matter what, even if we had to stall the pipeline and lose some time, right? Because if we rush, but our program is semantically incorrect, then it's of course it's no good. The result is worthless. So the compiler can arrange the code to avoid hazards and stalls. We have already seen how this is done. Of course, this requires knowledge of the pipeline structure. So we are going to look at different ways the compiler can help us avoid hazards and stalls. And so first, branch hazards. Remember, we were talking about the initial the initial design where the branch outcome is determined in only the memory stage, right? Because we know that branching depends on this 0 signal, which is one of the outputs of ALU. Okay, and before ALU computes this result, we don't know whether register 1 and register 3 have the same value, right? They have to go through ALU, get subtracted one from the other, and that's what would produce the 0 signal, which would remember then there is this AND gate with branch control signal, which is based purely on the opcode of the branch instruction and this 0, right? So we are taking the branch only if both it's a branch instruction and this 0 flag, if when they're both 1, right? So that's that's our typical initial scenario, and you see that we because checking if the branch is taken or not happens so late in the pipeline, right? We wouldn't know if we are taking the branch or not until the end of the EX stage, until the end of the third stage. If our prediction was incorrect, right? If we thought we would, so here the example assumes that we predict not taking, so that we predict that we will continue execution, and that's why all those instructions are going to be fetched and partially executed through in the pipeline, right? So this is AND, this is OR, this is add, right? Add is going to be will be being fetched at clock cycle 4, and we have to do that because until clock cycle 4 we don't know whether the branch is taken or not. Okay, so we just follow our prediction that the branch is not taken, and we execute all those instructions, AND, OR, and add. Of course, we push them into the pipeline. They will be at different stages of execution as of clock cycle 4, right? But they will be at at some stages of execution. And then imagine that it turns out that the branch is taken, and we have to jump to this offset 28 and execute this instruction. Okay, and what that means for our pipeline, it means that these 3 instructions, right, these things, they should have never been executed. So we have to eliminate any effect of these 3 instructions, any effect it might have had on the state of the memory or the register file. Luckily, since it's just 3 and none of those instructions have reached their MEM or WB stage, we are good. So we can just set the control values to 0 and just send these 3 instructions down there, down the sewage. So we flush these instructions because we basically say we eliminate any effect of those instructions, and they will continue execution just as as 3 bubbles. Okay, so of course we lose a tremendous amount of time. We lost 3 instructions because we had to turn them into bubbles because our prediction was incorrect. So so it skips over the instructions because of the branch. Correct. Yes. All right. So can someone tell me where this 72 is coming from? Why is this value 72? PC 72, yes. So those are values of the PC, right? I agree. So instruction 40, next one is 44. So this is the address in instruction memory where the instruction resides, and PC will go through 40, 44, 48, 52, and so then why 72? It's the all right. 40 and 28 is 68. If you ask me, 40 plus 28 is not 72. Exactly, it's plus 4. Remember, right? When we take this offset, all right, we already have PC plus 4, so it's PC plus 4 plus 72. So it should be 44 plus 28. So that should be 72 if I did my math correctly. So see how all things should kind of click in place, right? So this 72 is correct. All right. So reducing branch delay. This is something that we previously said, yeah, it would be a nice thing to have, and we assume that we have it available to us without really talking how this is implemented. Now things get more complicated. We are going to actually talk about how this is implemented in hardware. So their goal is to reduce their number of instructions wasted if we mispredicted a branch. And the way to do it is to know if their branch is taken not earlier than the end of the third EX stage. So ideally, we want to know it here at the end of this stage, right? How can we do that? We can do that because at the end of clock cycle 2, this BQ instruction will already know the values read from the registers, from the register file, from our 2 read registers. And if we throw in an additional hardware, we can actually make it compute the 0 flags separately, outside of the ALU, without the ALU. And it would be ready by the end of the ID stage. All we have to know is their target address adder and the register comparator, right? These are two of their things we need to get. All right. So first, register comparator to know if their branch is taken or not without involving ALU, and then to compute the target address so that we know where the control is passed. Okay. So here is another example, and in this example, why do we have 7 here? Can someone tell me? Right. So this is the BQ. Right. This is the example very similar to the example before, but why do we have 7 here? Because now it kind of doesn't make sense, right? 40 plus 7 is not 72, and even 44 plus 7 is surely not 72. 7 is the name of the branch method. No, because their 7th instruction. All right, how do you count 7? 1, 2, 3, 4. Exactly. So both people who said 7th instruction, 7 words, they're both correct. All right. So remember, in the actual BEQ instruction, this offset is saved as the number of words, right? So, and that's why when we decode it, right, we have to shift left by 4, right? So we take this and we shift left by 4. So shift left by 2 positions. So multiply by 4, it's 28. And now we see, all right, so it's 44 plus 28. This is indeed 72, and it is 7 instructions. So if BQ is a -1, this offset, it would jump to the same instruction, right? If BQ is 0, it would jump to this instruction, to PC plus 4. Right, so we can just go like that. 1, 2, 3, and then after 56, we're gonna have 60, 64, and 68. Right, so it's gonna be 3. It's gonna be 4, 5, 6, and this is gonna be 7. So we see, yes, indeed, it is offset of 7. Isn't that 7 line? Yes, because each line is 1 instruction, yes, it's 7 lines below the BQ. And you had hopefully had fun with this question on the test, right? So it was exactly exactly one of the things on their past test, right, with the BQ instruction. All right, so and here's our example when branch is taken. So this is their single cycle diagram. So we see that the things that are added is this IF flush. So this is to flush our IF ID register, because remember, our hazard detection unit was not touching the IFID register, and that's pretty much the only new thing here. Yeah, so this is actually the instruction after our BQ. Okay, so it needs to be flushed according to this, right? This is this end. It needs to be flushed. Okay, and because it was already fetched, so we have to flush it. So which means there's going to be one bubble, but then the next instruction after that is going to be our correct instruction, our LW, this one. Okay, in these two diagrams, all right, they are two two snapshots at at one clock cycle and then at the immediately following clock cycle. All right, so note all those values. Make sure you understand where those values are coming from, right? So here we are comparing registers 1 and 3. They're coming from here, right? Here we have registers 4 and 8. Why? Well, because EX is doing this instruction, the instruction before the BQ. So here we have PC currently has 44 because this is PC plus 4 for this instruction, right? This instruction is at address, again, refer to this, right? So the address of the AND is 44, so PC plus 4 would be 48, okay? And the previous value of PC was stored in the pipeline register, so it is 44. This is the PC plus 4 for the previous instruction, for BQ. All right, and from the instruction word, we have this 7, right? 7 is coming from here. So now, as you can see, it goes through shift left 2, as we just talked about. So this is your multiplication by 4, which yields 28. 28 plus 44 is 72. And through this multiplexer, this 72 travels all the way back, and here we have 72. So when branch is taken, and we know it is, this is the value. So this hazard detection unit is going to produce, reg write of 1, meaning that 72 will be written to our PC, and that would be the instruction that is going to be executed next. So we see it is indeed happens. 72 gets into PC, and then PC plus 4 is going to be 76, and then we have 72 here because it is saved in their pipeline IFID register. All right, and then PC plus 4 from here will go into here, into our multiplexer, and you see why it is 76, because it's this 76. All right, and same for previous instructions, right? So for example, why is this 10? Well, because our sub is writing to register 10. So remember how we had this pipeline diagram in the previous lecture, kind of incorrect, and then we had to kind of carry over with us this write register all the way here, so that it could then be used to actually write to the register, right? And this is register 10, right? So when our sub instruction gets into this stage, right, in the next clock cycle, it would deliver 10 here, okay? But it's going to be next cycle, right? But at this clock cycle, right? Again, this is a single clock cycle. This is a snapshot. You need to understand why this 10 is here. Okay, so this is extremely likely to actually appear on the exam, right? So analysis of all this, and why the values are. We might give you this diagram and just ask you to write values here and there that correspond to different instructions. Okay, so please make sure you practice. Take any sequence of instructions and just try to fill in all the possible values next to all the arrows. That would be a good exercise. All right, and so data hazards for branches. If a comparison register is a destination of the second or third preceding AIL instruction, we might actually have a data hazard on the BQ instruction. Okay, it's no different. So here we are writing into 1 and 4, and here we are reading 1 and oops. reading 1 and reading 4. So that's a hazard. Luckily, we can resolve this hazard using forwarding. Okay, so here is an example, right? If a comparison register, on the other hand, is a destination of a preceding ALU instruction or second preceding load or of the preceding ALU instruction or second preceding load instruction, we need to stall. We cannot resolve it by forwarding. Okay, so this is this right here and here and here and here, right? So we need both for this BQ, which means we cannot just resolve it with forwarding, right? As this example shows, right? We need this value here and here, and that means that we're gonna need to stall for 1 cycle. So just compare these two examples, right? So here, our instructions that write to those registers were the second and third preceding ALU instructions, and it was fine. We could go around the hazard using forwarding. If we have either of the following, right? If either the add is immediately preceding BQ or LW is the second preceding instruction before BQ, then we cannot resolve it by forwarding. We would have to stall. And finally, obviously, the worst case is we have LW immediately preceding, and that means that we need to stall 2 cycles. There's no way we would be able to avoid it, no matter whether we use forwarding or not. Okay, because this value is not going to be read from data memory until here, and even if we added the additional hardware for BQ to determine the result, the comparison between 2 registers at the ID stage, we need it at the ID stage, right? So there's no way we could, right? So it works now, right? Because we inserted 2 bubbles. Okay, and now we see that the dependency goes forward, right? Otherwise, if we remove these 2 bubbles, the dependency would go backward in time. Okay. All right. So dynamic branch prediction. And we are getting into kind of more complicated stuff, so we are probably not going to be spending as much time on it. I know just a general understanding of what's going on is important. Remember, we mentioned static prediction and dynamic prediction, branch prediction. So dynamic branch prediction will need some memory to keep the history table, and that would be the branch prediction buffer. It will be indexed by the recent branch instruction addresses. So we have all the branch instructions present in the table, and it will store their outcome, taken or not taken, okay, for the last, for the count of outcomes. So to execute a branch, we would check the table and see what our current prediction tells us, right? If there are more votes, if there are more cases in the history when the branch was taken versus not taken, we would expect the same trend to continue. And then we would start fetching the instruction accordingly, right? If we predict that it's taken, we branch the instruction, after computing the target address. If we are wrong, if our prediction, didn't pay back, we have to flush the pipeline, and we flip our prediction, or we change the count of our prediction. So why do we say flip or change the count? Because the simplest form is, we have taken, not taken, just like that. 1, 0, we predict that it's going to be taken. If we are incorrect, we flip it, and we say, now we predict that it's not taken. So really, we only need 1 bit, right, which we call like P prediction, where we say, let's say, P of 0, we predict not taken. P of 1, we predict taken. It's very simple. right? It's not very sophisticated, but and it's going to be, not very reliable, but it's very simple, and it only takes 1 bit, so it's very low on memory. As compared to if we implemented it with more bits, we could have actual counters taken, for example, 3 times, not taking 1 time, for example. Okay, but then the question, of course, is how many bits we dedicate. If we only dedicate 2 bits, we're gonna saturate this very soon, right? We're gonna have, both T and not T at 3 and 3, and it's gonna be useless. So we will need to every now and then to clear the history, to clear our accounts, so that we are no longer in a saturation mode, or we would have to use more bits for those counters. Of course, more bits means more memory. All right, and just scrolling. What is the best time to clear that history? It's not a trivial question. So best time would be when at least some of the counters are already saturated. But when you clear the history, you get rid of all the history. Okay, so typically, you clear the history for all branch instructions. So you kind of start from fresh. So it's not an easy optimization question. That would be my short answer. All right. So 1 bit predictor that we just discussed. It's simple, but it is not very reliable. Here's an example where it would mispredict twice. All right. So in this loop, we have, at least it's a nested loop, right? So we're gonna have a branch for the inner loop, a branch for the outer loop, and we know that we will cycle through the body of the inner loop, and then imagine you go up, stay in this loop multiple times, so the branch will be taken. But then when you are done with the inner loop, the branch will be not taken. So if you predicted it was taken, you would be mistaken. All right. And then you go with the outer loop counter. Okay. And then, you start executing the body of the outer loop, and then invariably you jump into the inner loop again. And then your first prediction would be based on the previous one, which was the branch is not taken because you flipped it when you were done with the inner loop. And now it means that you on the first iteration of the inner loop, you will mispredict again, because you will predict that it's not taken based on your last attempt, and it's actually going to be taken. So you're gonna have mispredicted twice on the inner loop, and that, of course, is a problem. So we can do a 2-bit predictor, right? So basically, it's there. So here is something hopefully familiar to you from Fox, right? So it's a finite automata. Yeah, it's a DFA exactly, and so we can just encode our states, right? So we can say, 0, 1, and like 1 0 1 1, right? So we need just 2 bits to encode all those states, and you see how this method is a lot more, much better, because it will mispredict after 2 mistakes, right? If you only make 1 mistake, you predict that it's taken, but it's not taken, you switch to this state, predict taken, you still predict taken, right? So only if you mispredicted twice, you were predicted taken and you guessed wrong once and you guessed wrong twice, only then will you flip your prediction from taken to not taken. So it takes 2 mistakes, 2 mispredictions, not one. So it's a lot more stable. And here's the pop quiz for you, the pop quiz number 3 for today. And so apart from determining whether the branch is taken or not, we also have another task, and that is to calculate the branch target. Okay, so if we know that the branch is taken, we need to know where to jump, where to branch. So we need to know this target address, and that would, of course, require also additional hardware, right? So 1 cycle penalty for a taken branch, and we need to introduce a branch target buffer. So we would have to cache their target addresses. It's going to be indexed by their address of the instruction as before. And if we hit and instruction is branch predicted taken, then we can fetch the target immediately. If not, all right, we mispredicted. It's we are out of luck. So that was that. And we have about 3 minutes, so let's really quickly talk about exceptions. And I'm going to skip the rest of the material because it's largely, more advanced. Well, not even more advanced, but just additional material with examples from specific architectures, which I can leave for your own reading, and we're not going to even include it on the exam. So, just read it. Please still read it, but the rest of the chapter. Just use it to enrich yourself. All right, so exceptions and interrupts, basically they correspond to some error condition that we want to be aware about. For example, incorrect opcode. Like if you try to actually execute problem 4.5, the opcode that is given in problem 4.5 is incorrect. If you try to execute it, you would get the case when, it's not a valid opcode. And the system has to do something about it. And it does so by raising an exception. Another example is an overflow, or syscall is actually implemented as an exception. And exceptions are managed by yet another coprocessor, which we call CP0. Remember, we also dealt with CP1, which was responsible for floating points. CP0 is the coprocessor that is responsible for handling exceptions. So when we have an exception, the control flow will change to the handler of that exception. The handler is a piece of code that responds to this exception, and so it's a little similar to JAL. So we need to save the result, save the state of the PC, so that we can return to the program that was executing when the exception happened. So we need this exception program counter. So it serves the role of an array. And then we just jump to the handler. There are different ways to organize their exception handling using either a master exception handler, like in this example, or by having vectored interrupts. So by having a separate handler for each of the exceptions. For example, for the incorrect opcode, it would be their handler would be at this address in instruction memory. For overflow, it would be here. And of course, you see there, so this is called a vector table because it's like a table of addresses that point to program locations. And so among the actions, we could restart or we could terminate the program. So it depends. As far as the pipeline is concerned, we need to basically make sure that it's like a branch that we didn't predict. Okay, so we need to complete their previous instructions, clear out the pipeline, then flush their offending instruction, like the add instruction, and all the subsequent instruction, and then branch to their address of the instruction that we got from their vector table or from that single handler, exception handler address. All right, and this is just their pipeline with exceptions. So you see that there's just a little additional added here, right? So this is the handler address, and that's it. No other major changes. All right, and here is an example. Again, what is flush doing? All right, so it's 1:51. I was hoping to be done with this chapter, but now, all right. So let's save it. Let's restart from their exceptions next time. All right, we covered it a little bit, but let's restart from this slide after the Thanksgiving break on Tuesday, and then cover exceptions and then skip the rest. But exceptions is important, so exceptions I'd rather not really rush. All right, that's all I have, and thank you for your time. Thank you for coming to this lecture. Hopefully it was useful. enjoy your weekend, enjoy your Thanksgiving break, and just a reminder, we're not going to have office hours tomorrow or Thursday or Friday. It's the break. So happy Thanksgiving, everyone. Enjoy the holidays, enjoy your break, and see you on Tuesday next week. Thank you.